chapters there are from the, actually, interesting. Yeah, we're going to start on chapter 15 as far as homework is concerned. It's chapter 21 in the new textbook. It's chapter 15 in the old textbook. So I need to correct that. So we're going to talk about electric forces and electric fields. Talk about voltages, electrical potential energy, current, resistances. So we're going to be using I'm going to try to use the Arduinos as much as possible this semester to cover pretty much through week 12. Week 13 we'll talk about light waves. And the last couple of weeks we'll talk about vibrations and sound. So this is called electricity and magnetism. So up to this point, we've talked about contact forces, which, that's something pushing something else physically. Actually what's happening on a molecular level is actually electrostatic forces, where you have the electrons from one molecule pushing against the electrons from the other molecule. So things never really touch per se, but because it's so close, we still call it contact forces. The non-contact force that we talked about is gravity, and it turns out that so here is the relationship for the gravitational force of attraction. Universal gravitational constant times the product of the two masses divided by the distance between the two objects, the center of the mass of the two objects squared. And gravity really only comes into play over long periods of time. You can have two things that are, we talked about that, was that one example about how long would it take for the space person to be attracted to the spaceship, and how long would it take for them to actually reach the spaceship. So they would ultimately come together. It took, I don't remember how many days, 15 days or something like that for that actually to happen. So things happen very slowly, or they happen more quickly when you have at least one of the two masses being huge. So, for example, we're not a huge mass, but the Earth is a big mass, and so we can see, we see the effect of us falling, being pulled towards the Earth. Now, back in the ancient days, besides observing gravity, they observed this property of attraction or repulsion in the case of electricity between various objects, and they probably just came upon the concept accidentally, like static electricity in your hair. They still had static electricity in their hair back then, and thought, why is my hair being lifted up like this for some reason? They're wearing their wool tunics or whatever, and they're rubbing those wool tunics up against something and generating some static electricity. So they tried, and then they found out that if they take certain objects and rub them together, that they can create this static electricity. So we know a little bit more about it these days. Ultimately, what you end up with is objects can either have positive charge or negative charge. Gravity, they don't really have charges. Gravity is always an attractive force. There's no repulsive gravity force. But when it comes to electric charge, you can have attraction or repulsion. So in general, what we have is things that have a negative charge, and which we nowadays know is due to electrons, an excess of electrons. And then you could have a positive charge, which is due to a deficit of electrons. If you have the same number of electrons as protons, then you're neutral and you don't have any net charge, and you don't see any of these kinds of attractive forces. So, as a mechanical engineer, I took very little chemistry. I did learn about combustion, But the actual chemistry I had as a freshman, and then not much more after that. So I have been reading a chemistry book. I think it's the chemistry book you guys use for your chemistry class, just kind of as a review of chemistry. And it's interesting because you got the chemistry book I think you used last year approaches the whole idea of chemistry from a different perspective. But does anybody remember anything about when you have chemical bonds, whether they're a covalent bond or what's the other kind of bonds? Ionic bond. So what happens when you have an ionic bond? Does anybody remember?
That's the one where you have two of different charges.
Yeah, so you have certain elements that have an extra have one electron in their outer electron cloud, or whatever you want to call it. Something like sodium, or what's another one? Magnesium. And then you've got things that have 7, or just they're one shy of having a complete.
It's the octet rule.
Yeah, the octet rule. So you got 7. So something like sodium, which has one, sodium has a deficit of electron. It needs one more electron to fulfill the octet rule, and then you have something like chlorine, which has, is that the right way am I going here? No, sodium has one extra electron. It has one on the outside, and so the electron from the sodium goes to the chlorine to get the 8, and so the sodium is a positive ion, and the chlorine is a negative ion, and that difference in charge attracts them together and creates an ionic bond. Whereas a covalent bond, they're kind of sharing an electron. But one thing I hadn't read before was the reason, because of this sharing of electrons, that the two elements in that molecule can be closer to each other, so that you have a reduction in potential energy, and that reduction of potential energy associated with the covalent molecule being more compact is what results in the chemical energy that is used, that we use or we put into things. Back when I did it, you just learned that you're sharing this electron and you had a different energy state, but why was that energy state lower or higher relative to them being separated from each other? So that was kind of interesting. A lot of it came back to the physics of the situation. Okay, anyway, so we have electrons, or something that has an excess of electron has a negative charge, and a proton, or something that has a deficit of electrons having a positive charge. And what we find is that experimentally, that if you have two positive charges, they have a repulsive force between them. If you have positive charge and negative charge, they're attracted to each other like gravity, and if you have two negative charges, they're repelled at the same time. So it's a little more complicated than gravity because it's not always attractive. Sometimes it's repulsive and sometimes it's attractive, and it depends upon the sign. If they're have the same sign as far as the charge is concerned, then they repulse. One thing about charge, too, is that it can be quantitized. And what that means is that there's a minimum value of charge that we deal with. The charge of an electron or the charge of a proton, which turn out to both be the same magnitude but in opposite charges. So an electron has a charge of negative 1.60 times 10 to the minus 19th coulombs, and the charge on a proton is 1.60 times 10 to the minus positive 1.6 times 10 to the minus 19th coulombs. We've got a new unit. So the units for charge are coulombs, named after Mr. Coulomb. Obviously, when they derived the unit for coulombs, they didn't base it upon the charge of electrons or protons. They based it on some other standard, which, if you think about current, we talked about current when we were talking about Arduinos. The units, we'll talk more about it, but the units are amps, and amps are coulombs per second. And typical in an Arduino, the currents are in the order of magnitude of milliamps, which are thousands of amps. Anyway, charge is quantized, so you can't have anything. You can't have a charge of negative 0.8 times 10 to the minus 19th coulombs. They're always in increments, exact increments of that. Okay. Then you've got certain materials that have a tendency to allow the movement of electrons through them, and some that don't allow the movement of electrons through them. So insulators are materials that don't, so let's see, so write this down. So I'm going to say insulators are materials that don't allow movement of electrons, and conductors are materials that do. That readily, I'll put readily, again, I was reading this in the chemistry book about, it's materials that have electrons that are not tightly bound to the atom, as well as them creating a matrix structure like iron, like metals, that also make it conducive. So it's the extra electron, but it's also the way that the material is formed into a solid, because typically conductors don't have to be solids, but a lot of times they are. Okay, so we have insulators and conductors. It just relates to how well the electrons can move through the material. Okay, now we're going to talk about how you can charge an object, how you can create it so that it has an excess of electrons or deficit of electrons. And there's two ways of charging material. One is charging by conduction, and one is charging by induction. So let me actually get something to show you here to demonstrate, so you don't just see a picture of it. And actually today, I wasn't planning to do this initially today, but because it's a nice, cold, dry day, I'm going to go ahead and, because I don't know when the next cold, dry day will be. Okay, so it turns out that certain materials give up electrons easily, and some materials attract electrons. So again, all we're doing is transferring electrons. So when you want to charge something, so here what I have is a aluminum sphere, which is then mounted on an insulator. So this is so that if I put any extra charge on this conductive material, that it doesn't conduct down through here, it just stays on the sphere. So if I were to rub this, and I can't remember exactly which one does it, but let's say I rub this rod with this little bunny. Let's say that it strips some electrons off of, well, let's say it puts some electrons on this tube. So now this tube has excess electrons on it. Now if I take this over here, what would happen is that the negative charge on the rod would cause the electrons to repel the electrons that are in the conductor. And so the negative charges would be pushed to the other side. I think I've got actually the other way around on this thing. Let me make sure I get this right. Yeah, let me just make sure I have the signs right. I'm not sure what I... Okay. So let's say I put some excess negative charges on here. Okay. So what'll happen is I'll take this and I'll put it near the conductor. And what happens is the negative charges here repel the electrons, so the electrons in the conductor move to the other side. So these repel the electrons, so the electrons go to the other side of so this side becomes negatively charged, this side becomes positively charged. Okay. And then when I touch it, because I have the positive charges over here and the negative charges there, they transfer the extra negative charges to the sphere. And then when I remove it, then this becomes charged with the electrons. So initially it's neutral because I have the same number of negative and positive charges. When I take this negatively charged rod and put it here, it pushes the electrons that are in the conductor to the other side because the electrons move freely. Now there's a deficit of electrons here. When I touch it, that deficit here pulls the electrons from here into there, and now once I remove this, the electrons become evenly distributed. When I take that away, they become evenly distributed, but there's an excess of negative charges on here. And you do the same thing. You take your material, rub the extra electrons on here. You take it over. These electrons would repel the electrons in the sphere, and then when I touch it, these electrons go to here and then become more negatively charged. And so you could keep charging up this sphere until it becomes more and more negatively charged. If this process here, instead of adding electrons to the rod, took electrons off, what would happen is this would be positively charged, which would draw the electrons to this side. Instead of being repelled, it would draw the electrons to this side, and when I touched it, the excess electrons over here would transfer to the rod, and then when I pulled it away, this then would have a deficit of electrons and it would become positively charged. So it's called charging by conduction because the charging happens when I touch the two rods. I touch the rod to the sphere. So let me just show you. I'll do it figuratively here. So here I touch them together. Then what happens is, because this is positively charged on this side, these electrons would then, these electrons would, they don't want to, I can't get the electrons out of there. Anyway, they would move over here and it would become negatively charged. Okay. Now, what you do in terms of charging by induction is you never touch the rod to the sphere. But what you would do is, say you have a positively charged rod and you put it close to the sphere, the electrons are going to be pulled from this side to that side. So this side becomes negatively charged, being attracted to the positively charged rod. This makes this side positively charged. Then what you would do is you would connect a wire to this side of the conducting sphere, and that would draw electrons in through ground. And so that would be called charging by induction, because I'm moving the electrons here, allowing the electrons coming kind of in the back door. So there's two ways of charging, by conduction and by induction. Now, this thing I have here is called a Van de Graaff generator, and what it does is it has a belt which basically does this process at a much higher rate than we could do with a rod. And ultimately this sphere will become charged, and then if I put any conductor close to that sphere, it will then, you'll see a spark jump across from here to my finger or whatever I have that if the voltage, if the potential energy per unit charge is big enough, it will cause sparks to occur. So we're going to play around with that for just a minute, because it's fun to see the sparks fly. And you guys can have a chance to try it yourself if you feel so inclined. Hasn't killed me yet. So what's going to happen is I'm going to charge this thing up, and I'm going to use this sphere because this allows the spark to be more intense. And then basically what's going to happen is that, I've got my boots. I'm not sure how these boots work. These may be fairly, I might have to take my boots off. But what will happen is the charge will be transferred through my body to ground when this thing gets charged up enough. And hopefully I don't blow anything apart. Okay. So I got to turn this thing on. Okay, so what's happening is there's an excess of charge being built up in there, and I'm going to turn this off so we don't see the... Yeah, so it takes a little while, a few seconds for it to charge up. The cool thing is that you can actually see the spark go through this insulator, because this is an insulator, but it doesn't mean that charge can't flow through there. It just can't flow through there easily. Weak. So what's happening right now is the charge is going up to there through my body, and nothing's building up, so it's not really too exciting. So you got to give it a few minutes. And I'll go ahead and turn the light out so you can see the spark a little bit better. And I'm going to take my shoes off to see what difference that makes. What will happen is if the humidity is high, it will dissipate the charge. It won't get to quite as high of charge value.
Turn your flash off, you silly Billy.
Was that bigger? Yeah. So partially that's because, so my feet are good conductors. Anybody want to try this? Okay, don't. So just hold it by the.
Ah! Yeah, I did.
Anybody else want to try it? Yeah, those are my shoes. Don't put my shoes on.
No, they're was.
How was it? Oh.
It was therapeutic.
It's therapeutic, yeah. So we'll do one more here. Ooh, that was pretty good.
There's no pent-up stress. You can just go out.
Yeah, that's right. It's shocking.
Dr.
Yeah.
What's the difference with the big ball?
Yeah, the big ball, yeah, let me show you the big ball. So you do have a longer insulating rod. So let's just see what happens. Yeah. So the spark isn't any stronger. And actually, let me just turn the light on so I can tell you what's going on here. So when you take your conducting rod here, this is a conductor, so the electrons are free to move. So I think this is actually positively charged instead of negatively charged. So because it's positively charged, what will happen is the electrons will move from being distributed evenly to being right here at the nearest part between the two objects. So as I get closer like this side becomes more negatively charged and this side becomes more positively charged. And if I did it like this, I don't know what would happen. Probably nothing. You just won't. You just won't see the spark. I mean, you'll see the spark there, but you won't see it through the rod. Yeah. So it's really nothing. This just by holding it here, all it does is it lets you see the spark through here as well as through the other part as well. What's that? Oh, we're all the way from the base? Yeah, probably. Yeah, it's pretty weak. Yeah. I'm not sure why that was. Anyway. So let me turn this thing off, which I'm going to turn off with a yardstick. For some reason, that always bothers me. Now, one thing is that if I were completely insulated from the ground, then you couldn't have and the distance between me and the ground was large enough, I wouldn't get that spark. You have to always have a path for electrons to flow to create a spark or to have current, as we found out when we fool with our Arduino. If we don't have the wires connected up so there's a path for the electrons to flow, nothing exciting happens. There we go. So here it's going to discharge. Okay. So what I have here are 6 aluminum pans. So what will happen is you will, if you turn it on, what will happen is that the pans will become charged. Let's say they become positively charged. So if they're all positively charged, they will repel each other. So what you'll see when I turn this thing on, they'll get charged and then they'll start to flip off. They'll start to flip off the top of the Van de Graaff generator.
I'm just posing for it.
Yeah. Right.
Is there an Indian graveyard around here?
Yeah, that's right. So magic. Yeah, so we'll do that again. So you can pretend like you're a magician. You want to pretend like you're a magician there? Yes. Is that an, okay, I'm going to tie my shoes here before I hurt myself. So qualitatively, what we've seen is that you can charge objects by moving electrons, either removing electrons or putting electrons in, excess electrons. What else have we said? We've shown that charges equal or the same sign charges repel each other. That's our CAN example. Okay, let me turn the projector back on. Okay, now we're going to quantify some of this stuff. So the law that governs the attractive or repulsive force between charged particles, it's called Coulomb's law. So if we ever have another cold, dry day, remind me, we can pull out the Van de Graaff generator and play with it again. But Coulomb's law says the force between two charged particles is equal to a constant, which we call K, and this Coulomb's constant, times the charge on one object multiplied by the charge on the other object divided by the distance between the two charges squared. So it looks pretty much like the law of gravitation, except instead of having masses, we have charges. But we still have a distance. The sign of the charges governs whether it is attractive or repulsive. And Coulomb's constant is 8.99 times 10 to the, I think it's minus ninth. No. What is Coulomb's constant? I forgot. I'll look it up. Might be 10 to the ninth. Ten to the ninth. Yep, not 10 to the minus ninth. And the units are newtons meters squared per coulomb squared. And you can, well, it's because this thing's not quite right. So the way I remember that is newtons, newtons meters squared divided by coulomb squared. So just you go back to the basic equation. It's still newtons, yeah. Right. So here's an example. So you've got two charges. Let me put this on one page. So here we have two charges, and they're separated by a meter. One charge is positively charged. It has a charge of 2.6 or 2.0 times 10 to the minus 6 coulombs, and charge 2 has a value of negative 3 times 10 to the minus 6 coulombs. And because of the fact that they're opposite signs, they're attractive forces. Now, right now we're just going to talk about the magnitude. You know, how big is the force? So if you use Coulomb's law with those values and you plug those in, let me just zoom out a little bit here. What you'll end up with So you'll put in Coulomb's constant, which is 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. The two charges, which I've made them positive by taking the magnitude of them, 2 times 10 to the minus 6 coulombs and 3 times 10 to the minus 6 coulombs divided by 1 meter squared, and you get a force of around 0.054 newtons, which is, you know, it's small, but it's not minuscule. But, you know, the Coulomb's constant is, remember, universal gravitational constant was something like 10 to the minus 11th. So these forces tend to be the ones that, with reasonable size objects, reasonable charge objects, can give you a reasonably large force without having, you know, massive charges to have that happen. Like with gravity, you need to have at least one of the masses to be huge for the forces to be of any consequence. So that's the easy part, you know, plug them into the equation, you get the answer. So the thing is that Coulomb's law can be seen as a vector equation. So I'm going to show it as a vector equation. It's a little more complicated. So the force vector is equal to K times Q1 times Q2. I've taken off the absolute value, divided by R squared, and then you multiply by the position vector divided by the magnitude of the vector. So this part of the equation gives you the magnitude of the vector, and this gives you the direction of the vector. So this little part, the R vector divided by the length of the R vector, this is called the unit vector. Whoops, sorry. So it's a unit vector in the direction of the positioned vector. Since we're not doing calculus-based physics, we're not going to get into, you don't have to know how to do this, but it's kind of showing you, to remind you that the force that we end up with is a vector force. And there's two ways of dealing with vector forces. One is to use vector algebra, where you use i's and j's, you know, the unit vectors and the coordinate directions. The other way is to take your force value and break it up into the components using geometry. So the algebra way is to use geometry. The calculus way is to use dot products and other more complicated stuff. Okay, so we already talked about that. Let's move on here. So let's look at another example that's a little more complicated than the original one. So we actually have three charges. We have two positive charges and a negative charge. And the question is, what is the force on the third charge due to the other two charges? So I'm going to give some numbers. We'll call this object 1, we'll call this object 2, and we'll call this object 3 here. And we'll say the charge on object 1 is it's positive, so we'll say it's 1.5 times 10 to the minus 6 coulombs. The charge for object 2 is going to be negative 2.0 times 10 to the minus 6 coulombs, and charge 3 is equal to positive 4 times 10 to the minus 6 coulombs. And the question is, what is the net force on charge 3 due to charges 1 and 2? Question mark. Now they're all in a line, so that makes the vector part easy. We just have to worry about whether the sign associated with the interactions are positive or negative. And we can do that by just looking at just like we did with forces, you can say the net result is the sum of the individual effects. So what we're going to do is we're going to look at the force between charge 1 and charge 3, see whether it's positive or negative, and we're going to look at the force between charges 2 and 3. And then we can add the two values together to give us the net effect of both the charges. That's called the principle of superposition, which we've used before. So the procedure is we're going to use Coulomb's law to figure out the magnitude of the force. And then we'll use the fact whether they're like signs to say the repulsive forces or opposite signs give us a force of attraction, and that'll give us a direction. That'll be the vector part of the equation. So, and we need to put some distances. I didn't put the distances in there yet, so let's do that. So we need to know how far these things are apart. So we'll say between these two is, we'll say that's 1.2 meters, and the distance between these two charges is, we'll say it's, this is not to scale, 2.0 meters. So you have to use subscripts to kind of describe what's going on here. So the way we would do this, if I used, we just have to be consistent about how we define this. You can define it. So the force on charge 3 due to charge 1. So that's what that stands for. So say F31 is the force not farce, force of charge, force on charge, let's put that right here. Just got to be consistent. Force on charge 3 due to charge 1. And if we do F32, that's going to be the force on charge 3 due to charge 2. So we'll say that the magnitude of 3,1 is going to be equal to K times the magnitude of charge 1 times the magnitude of charge 3 divided by the distance between the two objects. So Coulomb's constant is 8.99 times 10 to the 9th newtons meters squared per Coulomb squared. Q1 is 1.5 times 10 to the minus 6. It's positive, but it doesn't matter in this case because we're doing the magnitude. So it's positive. And then we multiply by charge 3, which is 4. So that's 4.0 times 10 to the minus 6 coulombs divided by the distance is going to be 3.2 meters. And we're going to square that. So we plug that into our calculators. And so I'll get 0.00527 newtons. And the question is it going to be to the left or to the right? Well, because charge 1 is positive and charge 3 is positive, they're going to be repulsive. So the force due to charge 1 on charge 3 is wanting to push this that way. So it's going to end up with a positive sign. So we could say, if we want to just use the sign to show the vector nature, we could say the vector force 3,1 is going to be positive 0.00527 newtons. And this comes from the fact we have two positive charges with the repulsive forces, and this is positive. So that's how you get the positive part. Okay, so let's add a page here. Now we look at the next one, which is, so the magnitude of the force on charge 3 due to charge 2 is going to be equal to Coulomb's constant times the magnitude of charge 2 times the magnitude of charge 3 divided by the distance between 2 and 3. And Coulomb's constant is 8.99 times 10 to the 9th newtons meter squared per Coulomb squared. Q2 is given as 2. It's negative 2, but we're going to use the positive part. So it's 2 times 10 to the minus 6 coulombs. Q3 was 4 times 10 to the minus 6 coulombs. And the distance between the two is 2 meters. And we square that. And we plug that into our equation. So we've got 2 instead of 1.5, still 4. Distance is 2 instead of 3.2. So what I get is that the magnitude of the force is 0.017, actually 80 newtons. And in this case, we have a negative charge and a positive charge. And so those are attractive forces. So the force, this is object 2, this is object 3. So they're attracted to each other because they're opposite signs. So the vector of force on charge 3 due to charge 2 is going to be negative 0.0180 newtons. And so the net force, so our net vector, the net force vector on 3 is going to be equal to the force vector of 3 due to charge 1 plus the force on charge 3 due to charge 2. And so we had, this one was positive, or that, yeah, that one was, this one was negative, so this, yeah, we got it there, okay. So this one was positive, so you have 0.00527 newtons minus 0.0180 newtons. And so the net force, 0.057 minus 0.0180, and you get that equal to negative 0.0127 newtons. Is that right? Yeah. So that's the net force on that one. So the one that's closer is, it's a bigger charge and it's also closer. And so this one was the one that kind of dominated to some extent, not super dominated, but it did. And so because this is negative and this is larger than that one, it ends up being a negative result. Okay. Now you get more complicated. We'll do one of these in class on Wednesday to give you a practice. But since a few of the students are not here today, I'm not going to hand that out till then. So the next case is where you have the charges not in a row, and you have to worry more about geometry. In this case, we actually just have 2 charges, and so it's not super complicated. What we have is we have 2 positive charges. We have charge Q1, which is 2 meters down from the vertical position of charge 2, which is 2 coulombs. So these are coulombs. And this charge 2 is 2.5 units in the x direction relative to charge Q1. And because they are both the same sign, they're going to be repulsive. This blue thing represents the vector or the distance between the 2 objects. So you'd have to use the Pythagorean theorem to find out what the length of this hypotenuse is. So that's where And secondly, because they're the same sign, they're going to be repulsive. So the force on this charge is going to be this way. So it's going to be up to the right, and this one's going to be down to the left. They're going to be exactly opposite because forces always come in pairs. That's what Newton's third law says. So let's just deal with two of them to start with, and then we'll talk about how you would define. So there's two things we've got to do. We've got to find the distance between the two. So that is going to be just equal to 2.0 squared plus 2.5 squared. Take the square root. So the straight line distance. So take 2 squared plus 2.5 squared. Take the square root of that, and you get that the distance between the two charges is 3.20 meters. Then you can use that distance to find the force between the two charges. And so the magnitude of the force between the two charges is just equal to Coulomb's constant times Q1 times Q2 divided by R squared. So we have Coulomb's constant, which is 8.99 times 10 to the 9th newtons meter squared per coulomb. We have 2 coulombs, and we have, actually let me get in the right order here. So this one's 3, Q1 is 3, Q2 is 2 coulombs, the distance is 3.2 meters, and we plug those in. Well, that's a big number. Did I do something wrong? That's why we use microcoulombs. Okay. So the force, the magnitude of the force between the two objects, yeah, that's what it is. It's big. 5.3 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the 9th newtons. Okay, so it's a very big number because I use coulombs instead of microcoulombs. If I use microcoulombs, then you'd have 10 to the 6, negative 6 squared, which would be 10 to the negative 12th. And then you'd end up with numbers that are similar to what we had in the previous example. Okay, so that's how you, the direction. Yeah, the direction, so let's do that. You have to figure out the angle, basically. And the angle in this case is just the angle between this hypotenuse and the adjacent side. So this angle here would be the same as this angle there. So that would be theta. So to find the angle theta, theta is just equal to the inverse tangent of 2, which is the opposite side, divided by 2.5, the adjacent side. Make sure it's in degrees, which it is. So if I take the inverse tangent of 2 divided by 2.5, I get 38.7 degrees. So we could say the vector F12, so this is the, actually let's do 2,1 instead. So the force on charge 2 due to charge 1 is, we'll say, has a magnitude of 5.3 times 10 to the 9th newtons and a direction of 38.7 degrees relative to the positive x direction. So so it's going to be, this force is F, this is going to be F21, so it's going to be pushing to the right, so it's positive 38.7 degrees with respect to the positive x direction. So I'm just using the magnitude and direction to specify the vector. And F12 would be the same magnitude, but it would be in a direction that would be, however you could say 38.7 degrees relative to the negative x direction, or something like that. Okay, so that's easy. Now, in this case, what if we have three charges that are not in line? How would you figure out what the force of the two other charges are on the single charge? So we're just going to do this qualitatively right now. If I wanted to ask the question, so what is, if I want to know what is the force vector on, let's call this object 1, we'll call this charge 2, we'll call this charge 3. So what is the force vector on charge 1 due to 2 and 3? Question mark. So if we look at this qualitatively, here we have two charges that are opposite in signs. So this is going to be an attractive force, and it's going to be in the straight line between these two charges. So this would be the force vector due to charge on charge 1 due to charge 3. These are the same sign, so that's going to be a repulsive force. So this force is going to be in this direction. So this is the force vector on charge 1 due to charge 2. Again, if I extend this, they should go through the centers of the other charges. And then the resultant force, so the total force on this is going to be, well, let me just copy this for a second. So clone that, move that down here. So there's the sum of those two, the vector sum of those two forces. So this would end up being the force on charge 1 due to the 2. So you've got this attractive force and this repulsive force gives you the net force. So the way we would do it is we would calculate the magnitudes of the interaction between these two charged particles and these two charged particles, and then we would use geometry to figure out what the components are. So you'd figure out the x component of this force and the y component of this force, and you'd calculate the x component of this force and the y component of this force. You'd add your x components together, which would give you the x component of the resultant, and you'd add your y components together, and you get the y component of the resultant force, and then you get and then that would give you the components of your resultant force, and then you could use the Pythagorean theorem to find the magnitude of the resultant force, and then use geometry to find the direction of the resultant force. So it gets a lot more complicated, and we're not going to have time to get through that today, so we're going to do that another day. But that's the basic idea of forces. It's just force diagrams, vector diagrams. So the last thing I want to introduce today is the idea of electric fields. So there we go. That's the next page. So we'll do some in-class examples of both of those. So the idea of an electric field is to think about a charged particle or a collection of charged particles, and if you then brought in another charged particle, how would that extra charged particle interact? So I'm going to use this as a charged particle, and this is a charged particle. So we're going to say there's an electric field around this charged particle, and we're going to say there's an electric field around this charged particle. And this charged particle you don't see. Okay, it's not here. So based on those two charged particles, I can come up with a electric field for each charged particle, and then I can add the two electric fields together to get a net electric field. Then if I bring in this extra charged particle, the question is, if I stick it this place, this position within the electric field of these original two charged particles, how is this charged particle going to interact? Which direction is the force going to go? Is it going to be pushed away? Is it going to be pulled towards them? Is it going to go that direction? So that's the whole idea of an electric field, is to have it so that if you have a given charged particle situation and you introduce, say, an electron, what's going to happen to the electron? Is it going to be repulsed, or is it going to be attracted? And which direction is it going to be attracted? So the way it works is you do that by basically going through the same kind of analysis, except rather than calculating a force, we're going to calculate a force per unit charge. So we have what we call this test particle, which is always positive, and it's really small. So basically it's kind of like, I'm there, but I'm so small that I'm not going to affect anything over here. So if you look at this scenario where you have a charged particle, and from this you're trying to figure out what the electric field is at some point, we calculate the force between this big charge value and this infinitesimally small charged particle, and then we define the electric field as the force on that test charge per unit charge. So let me just add a page. So here what we would do is we'd say the electric field, and it's also a vector, is equal to the force vector divided by this Q0, where Q0 is the test charge. So it doesn't really matter what the value of this test charge is. It's just a made up thing to allow you to calculate what the electric field is. So if we know how to calculate forces, which we do, and we divide it by the force calculation involves this charged particle, but then you cancel out the magnitudes in the calculation. So ultimately what you end up with is K times Q divided by R squared. So it's the same as Coulomb's law, except you only have one charge. You have your charge you're trying to figure out the electric field for, and you don't have a second charge anymore. The second charge cancels out because you're not calculating force, you're calculating force per unit charge. That's how you calculate electric fields. And you represent electric fields by arrows. The magnitude of the electric field at a point is going to be based on the length of the vector, and the direction of the arrow is going to tell you the direction of the electric field. So the simplest case is, what is the electric field around just charged particles, a single charged particle, not a multitude of charged particles. So let's look at that example. What does an electric field look like? I'll say around a positively So here's my positively charged particle. And here's my test particle, which is positively charged. So the question is, what would be the force interaction between these two? Well, they're both positively charged, so the direction of the force vector is in that direction. And because my test charge is always positive, what I can do is, once I've figured out that vector, I can kind of make that test charge disappear, and instead of showing a force vector, I'm going to show, this is my electric field vector. So what you'd find out is that all the electric field vectors around a positive charge are immediately away. They point away from the positive charge. So these are all going if I drew a straight line from here to there, they would just keep going that direction. And the closer you get to the charge, the longer the particle is. I mean, the longer the vector is. So this is the electric field, let's say, at these points. So what I'm doing is kind of like you've got a grid of points in space, and the question is, what is the electric field at those points? So I'm showing these as points, and they're all pointing away from the positive charge, and the closer you get, the longer the vectors get. And that's because the closer you get between two charged particles, the stronger the force is. It's equal to, you divide by r squared. So because you divide by r squared, as r becomes smaller, the electric field becomes larger. And as you get further, so here's let's just talk about this. Here's my positively charged particle. The electric field is pointing this way at this point. It's pointing that way at this point. It's pointing that way at that point. And as I go away, the vector, so here's my vector. As I go away, it gets shorter and shorter and shorter. And that's basically due to this term right there. So that's what it is with a positively charged particle. For a negatively charged particle, it's exactly the opposite. It has the same magnitude vectors, but they go the opposite direction. So let's do that. So we'll say negatively charged. So here's my negatively charged particle. My electric fields are going to look something like this. They're going to be pointing in because the positive test charge is attracted to the negative actual charge. And out here, the vectors get shorter, but they're all pointing in. So to find if I had both of these charges next to each other, so these were separate, but let's say now I have the two charges next to each other, what does the electric field look like composite-wise? We can almost figure out what it looks like. Here's the positive charge. These are pointing away. These are pointing towards it. So the electric field of the combined two charged particles looks something like this, where you have the vectors increasing. They're big here, they get a little shorter in the middle, and then they increase as they go. So the vectors are pointing in. Now the question is, one question you may have is the electric field just kind of like a useful tool, or does it really exist? It's kind of like gravity. Does gravity really exist, or are we just using this gravitational field to help us visualize visualize something that we can't visualize because it's not visualizable, and if that's a word. And the answer is yes, it does actually. An electric field exists around a charged particle. It's not just a tool. And the reason I say that is we'll find out later that light traveling through space is an interaction of electric fields with magnetic fields. And it goes, you have a star very far away, and it creates light. And that light moves through millions and billions of light years. But there's vacuum. There's nothing in there. There's no medium for the energy to be transferred. So the only way that could happen is if there has to be something there, and the something there is that you have these electric fields and these magnetic fields interacting with each other, kind of feeding one off of the other, and that allows light to transmit or propagate through space. So that's how I convinced myself. Initially, at this point, we think it's just some kind of bogus thing they make up to make it easier to understand the interaction between charged particles. But the answer really is that there is actually a field. Otherwise, we wouldn't have light. And we know light exists, so there must be a field. Okay. So, yeah. Electricity is, it's one of those things, trying to imagine all these things, because it's not something that we personally see. We see pushing cars down the road. We see balls flying through the air. We see water hoses looking like little parabola shapes and things like that. But electricity We don't have that visual connection, so it sometimes does get a little bit more difficult. So we'll try to work around that.
You can take the iron filings on a piece of paper with a magnet.
Yes,
and sort of
you can visualize. Yeah, it visualizes it. It's not the actual magnetic field, but it's a result of the magnetic field. And if you look at the filings on a magnet, they kind of look like that, which we'll find out why that is. So the magnetic field on a magnet looks kind of like a case where you have a positive and negative charged particle close to each other.